Welcome back. How's everybody doing? Really? Is it really good, or is it just like the American good? Like the... Actually, looking in this class, I think there's only one of us who's native to the United States right here, right now, apart from me, the two of us. I think you're native. So, yeah, I know the stereotype. How's it going? Answer is good. Unless you live in the South, and then it's actually how it's going, and you don't, never mind. So, should we have class today? How many of you are having a lot to do at this point in the semester? How many of you are regretting some of the choices you've made at this point in the semester? I don't have any way to help you. I'm making it worse, but I do have something. Those of you online, you know they can do this. Will this make it any better? Come on up, help yourself. Take as much as you like. For those of you online, I just dumped a big grocery bag full of candy. So any of you online, if you want candy, you'll just have to come to my office to get it whenever you're able to. So in the meantime, help yourself. It'll just be sitting here. When I'm done with class, I'll put it away. Take some for your friends. So now I have to admit, again, being a native of the United States, I wouldn't say this is like as good as the candy you get in your countries, probably. But, you know, cheap United States candy, why not? It could go worse, right? So that doesn't make this semester any less hard. It makes it hopefully a little easier to get through the day. All right. Everybody okay? Take a deep breath in. We're going to get through this together. Yeah. So I did try to lighten you a little bit. I did not give you a formative assessment this week. And then I just assigned a homework. But good thing about the homework. Homework 3 is assigned. You may have got a notification through Icon. You can find it on my website. I'll just pull that up real quick. Maybe. There it goes. The homework is something where you can do part of it now and part of it at the end of next week. It's due October 18th, so you actually have 2 weeks and 2 days. And it's the last homework of the semester. I'm just going to say that. There's the project, but this is the last homework. Okay? Okay. And again, it's in Markdown. I'm using the same data that some of you have Lisa's class. I'm using the data from her class. Turns out that was data I collected, or I was involved in the collection, that she used from me. So whenever you think I'm borrowing from her, stop that right there. I first used this assignment in 2006, or used these data in an assignment in 2006. Then she found it and wanted to borrow it from me. I let her, and now she's using it, so now I'm taking it back. So anyway, by the way, that class we had team taught when we were at Kansas anyway. So that's announcements. The next announcement. Basically, you're fitting what we're doing in this lecture here, confirmatory factor analysis, what we'll do in the next couple lectures, which is greater response type model for the data. And we're going to vary the priors, and we're going to look at distributions of latent variables. So that's what the homework is about. Okay? Great. Questions? No? Okay. My office hours are today 2 to 3. We have a GMAS meeting for ed measurement statistics, graduate students. Something about internships. So go find an internship if you want. I never had an internship. But then again, I've never worked in industry. Worked with industry a lot. Never with it. Anyway. Finally, as you probably know, I graded all your class projects. You probably have a variety of comments from me. Please don't be offended by my comments. It's just what I'm thinking as I'm grading them. If any of them struck you as being mean, I apologize. It was just blunt. I'll give you the nice in person. How's that sound? Okay? But some general notes. The next step is everybody needs to meet with me to talk about next steps. All right? There are 17 projects, that's 17 meetings. I'm willing to do it because I believe that you doing this with some data on your own will help. And the other part of that is, I think I put this in every one of your projects, almost everyone needs to define the model first with notation, because that's the core of what you'll be building in Stan with syntax. So in your meeting with me, we'll discuss how to do that. Before the meeting, if you want to try building your model notation, what is it you're estimating with notation, right? The actual notation itself, do that. But basically, we're going to work on building that together, okay? Okay, some general notes overall. Not everybody, this applies to, not everybody, but there were some trends in class I wanted to talk about. Number one, grammar. Look, most of us in this class are not native speakers of English, and that's okay. I actually think that's wonderful. And I also know that if I were to try to write in whatever your native language is, I'd be far worse at it than you writing in my native language. But that being said, I want to help you try to improve. Part of the reason I have a project is to provide edits to help you improve. And I just have some general tips that help me. I'm also pretty bad at grammar, believe it or not. My problem is I write too quick, and then I don't want to go read what I wrote. And so I put a hot piece of garbage on a page, and then I don't slow down enough to read it. So I'm going to give you that perspective. The other thing I was going to tell you is to use any and all online tools to check your grammar as you go. So what do I mean by that? And maybe some of you have some tips for this also. I have to admit, I don't teach grammar. Actually, the class right before us, I think, is an English language class. I don't know any of it. I know it from a native speaker. I failed it in high school. Seriously, you can see my high school transcript. It has an F in English, right? So, yes. So I don't know how that I can teach you, but I can tell you what I use to help myself, right? If you haven't seen it already in Word on the desktop version and on the online version, there is let me see if I can find a document. Nope. Well, let's just do this. This is the Mac version, but under Review, there's this editor button that you can press. It will read your writing and talk about syntactic issues. It's not perfect, and it especially struggles in technical writing, but it does pick up some of the issues that you end up getting, all right? So that's one way to look. The other thing I found very helpful, and again, I don't know if you have an issue with writing that's coming from learning a second language or a third language or a different language than you're used to. I don't know how helpful this is for you, but it helps me as a native speaker. And that is the read aloud function. I have Word read me my document for two reasons. Number one, it slows me down so I can parse each sentence. But number two, it will be reading and I'll be like, oh, there's something wrong there, right? And it brings me back to it. So just as a tip, try both of those tools. Even if you're writing in Markdown or something else, work in something like Word that has a tool like that, if you have that problem. And I'm telling you, I do this, and I'm a native speaker, so I especially want to give you the support otherwise. The other part I will tell you about writing, and again, I feel like an imposter talking about this because I'm not writing. I don't study how to write, okay? But I firmly believe the only way you get better is to keep doing it, right? So you have to write and write and write. Some people suggest writing in journal, like writing yourself a personal journal in English each day, just to try to practice. I think that is good practice. You could also just work on a document, right? If you're working on a paper or a master's dissertation, do a little bit each day to keep writing, because I think that practice helps. And then at some point, seek feedback on that writing, either through an online tool or through somebody else to try to give you some perspective with it as well. So anyway, that doesn't apply to all of you. But for those of you who are potentially struggling in English or struggling with grammar, myself included, that's what I do. So I hope you're not hearing this from a punitive point of view. I did not penalize you for it, but I tried to edit your document to give you that feedback also. Because there's first of all, there's writing in English, and then there's technical writing in English or scientific writing, And then there's writing in the field in which each of you is studying, right? And all three of those is another layer of difference that you don't learn otherwise. Okay? Any questions or thoughts? Anybody have any other ideas to share to how to get feedback or help? Yeah.
There's also a writing center.
There is a writing
It's
center?
not used often.
Oh.
And so I know they would be appreciative.
Absolutely. It's in the College of Ed, no less,
I
right?
think so. Either that or they might have merged with the other one.
In the university.
Yeah.
Yeah, if you look up U Iowa and Writing Center, you should be able to find information online.
Yeah.
It is tough. Look, I don't envy you. It's hard. Like, I have a hard time visiting. Well, first of all, let me separate. Everybody's welcome here. I want everybody to be encouraged and supported here. But if you're like me, writing in English, technical writing in English is a skill you don't even learn anywhere except for grad school. But then writing in English, if you're not fluent or not native speaker in English, all of you are fluent in English, is that much harder, right? I can't imagine what you're going through to be able to do that. And I have the utmost respect for you. But that being said, I want to try to help you. That's all. Okay? I hope is that a fair way of putting it? Hope I'm not trying to disrespect anybody here. Look, I traveled to Germany this summer, and I don't know how you do it every day. Like, it's just so tiring to be immersed in a language that's not your own. I know eventually you get a little bit more used to it, but it's very difficult, and I appreciate that. And I just want to let you know you have my respect and support, but I'm trying to get better as a professor teaching you how to write. Because each of you is in a degree program where you're going to have to write something to leave, right? So, okay? Okay. Does that help? Any other tips anybody else have? Any tips the non-native speakers may have that may help with their writing? Yeah.
Maybe for like the technical, what I usually do is I read papers that are related to what I'm doing and try to see the style that they use for writing.
Very good point. Yeah.
More like get the style of cool.
That sounds good. Yes. If you have an example writing in the area. So if you were to Google something about, like, we're doing factor analysis or whatever your project area is, if you see how they write about analyses in that area, that's a very good idea. Essentially a style guide. And let me just be fairly honest. I always rip on Iowa here, but let's talk about the English language. There's some serious problems with English, right? I mean, research, singular and plural. What? Right? But researchers, plural. You can be researchers, singular, plural. Anyway, right? It's like me and Duolingo have a love-hate relationship with it. Yes, I use it every day, trying to learn German and Spanish, and I've done French and whatnot. However, when the hints aren't right, it doesn't teach you anything apart from frustration. Right? Like in German, I can't tell the gender of a word without looking it up, and it doesn't tell me the right article that goes with it to understand it. And I'm like, oh my goodness, it kills me. But I still try. I still work for it. And I try to appreciate what it feels like to be in your shoes. So anyway. Okay, enough of that. Step 2. Study designs. Many of you had something about there was a non-Bayes method. I don't want that in the class stuff. And there's a couple of reasons for it. One is pragmatic. It's hard enough I want to help you with this building Bayes. So I want this to be a Bayes-focused project. Number 2, you can still do everything you're proposing in Bayes, you just won't have a comparison. That's fine, right? And then 3, once you get done with class, if you want to continue that research on your own, then you can add it. That's fine. But having it as part of the project, I feel compelled to try to help you with it. And just from a logistics standpoint, that makes my job a lot harder because, again, I have to make sure we keep track of everybody's project. And I'm doing it in Stan. It's a lot easier than everybody's project and then whatever package or the program you're using, right? So I have some comments in there saying just don't use Bayes. Don't use Bayes. What am I talking about? Don't use the non-Bayes things. Just don't provide the comparison. You can still do the research plan you are. I mean, the bare minimum for a project is a data analysis in Bayes, right? It's okay. But that being said, I do hope you get more out of it. So does anybody else have questions or comments on that? I can only help with Bayesian cod. That should be code. See, typo. Cod, a type of fish. Didn't know there were such a Bayesian fish out there. All right. So, big picture. Set up a meeting with me or come to office hours. Remember, office hours can get kind of crowded, but you have that link right there, jonathantemplin.com/meeting. Click it, find a time, we'll make it work, okay? Any questions on projects? I enjoyed reading it. I think each of you is doing something very interesting. I want to help you either flesh out the idea or implement the idea or get out of your way, depending on what you want. But I do think everything's going to work for class, okay? All right. Questions on anything?
So I think this is related to Bayes, but there was a debate between my friends when like the weather says there's like an 80% chance of raining. Does that mean that there's a 100% chance of rain in 80% of the area, or there's an 80% chance of rain, period?
Okay, so that's a technical definition from the National Weather Service. I'm a little bit of a weather geek.
Okay.
So the way the National Weather Service describes that is that measurable rainfall at a trace or more will fall within the county area, the warning area for each National Weather Service office, the forecast area.
Okay.
So what it would say, 80% chance is on 80% of days where there's an 80% chance, they would have measurable rainfall somewhere in their forecast area.
And do they use Bayesian
Yes.
methods to do that?
Yes. So there's in weather, they talk about climatology, and I don't know enough, I'm not on the technical side of it. But generally speaking, what is taken into consideration in a weather model involves the atmospheric conditions, but also what time of year it is, and then previous years similar. Now it's much more. It's not a simple process. They have models that are physics. I mean, like literally, like physical features of what's happening in the atmosphere, trying to predict what's coming and going with air masses and so forth. But there is part of that goes with it. Yes. So
interesting.
It's quite complex, but it's fun to watch. Read. If you, I have to do this now. I'm sorry. Maybe I don't. You know what? Never mind. Not on this computer. If you're interested, take a look at the National Weather Service forecast discussion. There's some real technical language in there. It's really fun to read. You'll know more about what's going to happen on a day-to-day basis. Like they debate whether or not the highs are too high for today or lows are too low. I'm serious. It's pretty cool to see. So, talk about a live data analysis problem, though, right? You know, another issue that's big in National Weather Service and weather forecasting is missing data. Because to accurately know what's happening in the atmosphere, you need to measure it at levels of the atmosphere. And believe it or not, in the United States, our National Weather Service offices release weather balloons with instruments on them that record wind, pressure, other information, temperature as it goes up in the atmosphere. And they do that twice a day. And those form a lot of the data points that are used in the analysis. However, that's still not enough. If you think about it, each weather service office is 150 miles, 250 miles apart. Right? So there's a lot of missing data. They use data from airplanes. They have surface observations. But how do you tell what's going on above you is a real big problem.
Wow.
So anyway, interesting data issue. If anybody wants to learn more about modeling, take a look at weather. So use that for it. All right, other questions? Life questions? What's this class again? All right, where did we start? Do you remember where we left off? It was fun.
We had done CFA.
CFA, or normal distribution. We were talking about the factor scores. Remember that? And I was starting to talk about, I have these slides here. Let's see here. Actually, I had a question from online about the meeting. You're welcome to book a 30-minute meeting, or I think you can go back and book a second meeting online if you want to do for more than 30 minutes. So I have it set up to do 30 minutes because I anticipate having a lot of meetings, and I do usually. So 30 minutes gives more slots, but you can do two back to back if you book one and then go back and book another one right beside it. Okay? All right. Hope that helps. Why is this so big? There we go. All right, so I made this lecture a number of years ago, but the math is still the same. I wanted to talk about these factor scores a little bit. All right, so here's our CFA model. where I had left off in the code, of course none of this is run now, but let me get this code warmed up real quick here. Here we go. It's going to take a little bit of time, although not that bad. I ran a stand model yesterday that took 3 hours, so it takes a while. Can be something that is difficult, but I wanted to show factor score distributions and talk about factor scores a little bit more, because I want you to think about that, particularly in the latent variable sense. Now, often in educational measurement, we aren't running CFAs, but we are dealing with factor scores, and they're the same parameter whether you're in CFA, IRT, or otherwise. So whatever I'm saying here, with the exception of the model form, will apply, like how we look at them, how we think about them. And I had a plot right here that looked at the expected value, or excuse me, the EAP estimate of the factor score. This is the mean from the Markov chain compared to the posterior standard deviation of the factor score. And you'll see this trend here, right? As scores went up, the factor scores, standard deviations got bigger. So it turns out this plot threw me for a loop. This was the fun thing with Bayes. Because if you learned all this stuff in frequentist land, you will learn that in a CFA model, the factor scores have a constant posterior standard deviation. But this is not constant, clearly. Right? So let's talk about why that is real quick. I'm going to give you some math. Sound good? This is important. I think it's important. Understanding the factor score, particularly if you're going into educational measurement, is critical, right? Because you'll keep saying that, you're in the business of selling scores. Those come from the factor score or some derivative of it, some use of it, like test information function use, right? So a factor score is an estimated value for this F, right? This is our CFA model. You see I've been writing it this way since 2015. Seriously, these are my slides from 2015. Somewhat of inter-rater reliability there, kind of consistent. Okay, so it turns out, it's funny, there's been a long resistance to using factor scores in the psych world because of something being called the indeterminacy of factor scores. Have you ever heard of that comment before? Well, indeterminacy means the factor scores are not unique. And if you're estimating, or if you're working in a model that's not confirmatory, if you're doing the full exploratory factor analysis, that is true. In a confirmatory factor analysis, scores are unique. The model is identified. There's no ridged likelihood, including in the posterior distribution, unless you specify some weird prior distributions where I don't even know what those would be. And it's funny about that because in some contexts, if you leave here and you want to work in an academic field, like if you go work in a psych department, this might blow your head open, right? You'll talk to your colleagues. I talk to my colleagues. When I used to work in psych department, I've worked in two, not for very long, didn't fit very well, but worked in two. And I've had these conversations talking about, well, we don't ever use factor scores because the indeterminacy of fact, we can't use those, right? Which is an old idea. So we talked about that with research if they wanted my help doing some type of research, quantitative methods in their research. But then we pile into the same the faculty meeting, and we talk about giving scholarships to students on the basis of GRE scores. And GRE scores are factor scores. So it's this odd dichotomy. So I felt the need to sort of build that. But the bigger picture of this is that the factor scores, I had these slides, but these are the factor score distributions. So yeah, I had this little, the point is I had Daphne, my daughter, helped me build this slide for a job talk. We were talking about where singers might be on some value of latent trait that was of interest. Taylor Swift, Miley Cyrus, and Justin Bieber. I still think this, after a number of years, this still holds up pretty much. Although maybe, I haven't heard much from Miley lately, have you? I know Swift is having a new concert tour next year, right? So I see some head nods of the Swifties in class here. Maybe I'm a Swiftie myself. Anyway, Lisa, not a fan. I, on the other hand, am a fan. That's okay. I'll admit it. I'll just be out there, okay? You can put that in my student evaluations. Class stunk, but at least he liked Taylor Swift. Right? Anyway, but the thing is, you get a score. The thing we often forget about it, although you don't, because I keep talking about in this class, is the error that goes with the score, the distribution that goes around it, right? So this is gambling. This is an example. These are actual posterior distributions of a set of factor scores when I used this gambling data before. These are 4 people. You can see how much overlap there are in those scores, right? The EAP would be the mean, and there's not one. So you look at the black line, the mean of that is just a little less than 1. You look at the blue line, the mean is a little over 2. The mean overall should be about 1. I'm sorry, the standard deviation should be about 1. So in theory, we think that these distributions should be somewhat far apart, but then you look at their overlapping part. Yeah, it's very much more likely the blue line and the black line. The blue line is more of the factor than the black line, but there's a relatively big overlap between the two distributions, such that there are any point after like 1.5, there's a chance the person with the black line, that score is actually higher than the person with the blue line, right? So remember this, error goes in scores. Error is in scores. And if we forget about the error in scores, literally everything we do with them could be screwed up, right? What do I mean by that? How much evidence do you want that one score is bigger than the other when you make academic decisions about somebody or job decisions about somebody, right? If you're in a credentialing situation, for instance, my family, every single one of them almost, my dad was. After my dad, everybody was a nurse. Like even my grandfather worked at a hospital, sort of as a nurse. My grandmother, both grandmothers, my mother, my aunt, both of my sisters, all nursing. And to be a nurse, a registered nurse, at least in California, and I believe in most of the other states, you have to pass a credentialing exam, right? It's something that's called the NCLEX. I don't know what the acronym stands for. But the NCLEX, each state decides what score you need to pass. And the way the NCLEX works, it's an adaptive assessment, that it gives out up to 350 items, I believe, over 300, so that some confidence interval of your posterior distribution of theta is on one side or another of that cut line, right? So it's making a standard of evidence saying that we're 95 or 90% confident that you're on one side or the other. It just takes a lot to do. And you compare that to what we do in academic decisions here in the university, right? Particularly I'm used to graduate admissions. Our program is all graduate students. We see GRE scores. Do we ever see a standard error with it? No. Where do those standard errors exist? There is a book called The Guide to the Use of GRE Scores, and it reports them generically. However, that's not the standard error that goes with each person's score. So when you have 2 scores, you have 2 people, and you're trying to decide between them. Now, usually for admissions, the admissions standard is different than like deciding on students we put forward for certain scholarships on campus. But we're trying to put people forward, but we're not considering how much overlap that might be. So a person with a total GRE score 320 sounds good. Maybe we favor them over someone with a total GRE score of 315. But if we factor in the error, what's the probability 320 is higher than 315? It's not 100%, not anywhere close to it, right? And I think that's the thing I want you to think about when you're talking about these factor scores. How are we doing? You get this in other places, right? Another part of that. How many of you take the EAP estimate and do stuff with it? I saw some of your project proposals. The logistic regression methods of diff. Ever heard of that? What do I mean by that? You take theta, you take some group variable, and you put it in a linear model, or a logistic regression, predicting each item, right, to see if there's an impact of the grouping variable as a main effect or an interaction with theta. But where do you get your theta? You get usually one estimate of it. That presents a problem, right? Because one estimate of theta doesn't describe the entire continuum of theta as well. So anyway, anything that you do with them, you have to remember the error attached. That's why, for me, Bayes works well, some way, right? Some type of error. And by the way, this is something we've been aware of almost since we've had psychometrics and IRT. I just don't feel like we teach it enough in our classes. So there's an assessment program called National Assessment of Educational Progress, NAEP, the nation's report card. You may have heard about it come out in the last week. You know, student scores are down 10% in math or something, or reading, right? You've heard those headlines?
Cool, new version of Nation at Risk. Great.
NAEP what?
Nation at Risk.
Oh, Nation at Risk?
I was
Yeah.
like, there's going to be a new version that we need the. Anyway, sorry.
Yeah, something like that. NAEP it's actually, first of all, a very nice assessment program. But I mentioned this in class previously. If you get their data, they don't give you 1 score for theta, they give you 5. Right? Those 5 values they call plausible values of theta. Now, the way they calculate theta is a little bit different than we do, but if we were to draw plausible values of theta, we would look at a person's posterior distribution and sample from it at random for 5 values. And then we would go put that in the weighted analysis to go look at whatever we wanted. Diff, prediction of other things, whatever. Right? Alternatively, why stop at 5? NAEP's 5 plausible values is a great paper by Miss Levy. I think it's 1992. I mentioned it in class also. Talked about the issues of sort of why we need more than 1 score for theta, particularly under NAEP, where we don't have a lot of items per student. We have a whole posterior distribution. Stan spits out the entire chain, right? Think of the damage we could do with 1,000 sampled values of theta. So I want you to think about that as you go through. When you take a mean of a parameter, particularly a person parameter, don't forget the error, right? Don't forget the error. Yeah.
So just to be sure, in this case, those colors represent subjects.
That's right. Different people.
Different people. Okay.
That's right. That's right. Oh, I had a quote from Pearson, but we'll forget about that right now. The main other thing I want to talk about this, we talked a little bit about factor scores, MAP versus EAP, right? EAP is the mean. Expected a posteriori is what EAP stands for. MAP, do you remember that? Maximum a posteriori, meaning the mode, the peak of this factor score distribution. And these are 2 hypothetical distributions. You can see if you use the mean and the mode and you have a symmetric distribution, they're roughly the same. And we've all taken basic statistics. If you have a skewed distribution, they're not, right? But remember this, not all factor scores are the same. So when you look at technical manuals of assessments, if you're in ed measurement, when you look at, or when you're not in ed measurement, if you're looking at psychometrics, personality measures, all that stuff, ask how they're getting their estimates. But here's one fun thing about factor scores. In CFA, we can derive the case and show that our factor score distributions will be normal in CFA. And the way we do that, I'll show you in just a few slides. But it comes from the assumption of normality for the factor and normality for error. When we put all that together, the other stuff are pretty much constants, and we get a normal distribution. Okay? How often are you using normal distributions for your item responses, though? I'm doing it in this class, but I think I told you, who would ever do that if you had discrete data? You shouldn't, right? Next week, we'll have the discrete data distributions that we need. But when you switch the distribution, so if you go from CFA to IRT, if we used a graded response model on these data, for instance, factor score distributions are not normal except in the limit. What's that mean? As the number of items goes to infinity, and the model fits the data, the latter part being really difficult to achieve as items go to infinity, the distribution converges to normal in distribution. Right? So just remember that if you're describing confidence windows around theta and you're using plus or minus 1.96 or something like that from a Z or from a Z table, there's no guarantee that distribution is normal also. Right? And so when you look at, again, small numbers of items, you might see a discrepancy between the maximum and the mean itself. things to worry about. Have you thought about this? Have people talked about this in other classes? No. Yes? IRT? Good. Anyway, let's go up to some distributions. Here we go. Here's our Bayes theorem right at the top. Here, the distribution of the factor given y, that's our posterior distribution. And it's from, we know that that's the distribution of the data given the factor times the prior distribution of the factor over the marginal distribution of the data. It turns out in CFA we can get each of those terms with some matrix algebra. Only in CFA. Only when all of the items have the normality assumption. All right, so for instance, we can see that for each item, conditional on the factor, we see each item follows a normal distribution, with the mean being what the linear predictor of the model would say. Right? Factor, item intercept plus loading times factor. And the variance being a unique variance right here. Right? Seems familiar. We coded that into Stan last week, right? You saw that. So we could put all these in matrices and see the same feature here. And if we ended up having more than one factor, it would look like this right here. So I'm just going to gloss over the matrix algebra. But I know some of you like matrix algebra. Some of you hate it. That's okay. I appreciate you too. Okay, matrix algebra shortens the notation though. But what we can see here is the following. What is the distribution of the factor itself? Well, it's normal or multivariate normal with some mean and covariance matrix. Although we usually have to pick an identification method to figure out what those means and covariances are. Usually we set the mean vector to 0. And for what we've seen in this class, we've had the factor with a variance of 1. All right, so the diagonal of that thing would be 1 for multiple factors. Now finally, for y, the distribution of y, we can actually show us, again, some matrix algebra using multivariate normal distributions that the distribution of the data itself under a CFA model is normally distributed, multivariate normally, right? So what am I talking about? In the analysis we have, in the R code we have 10 items. What's the joint distribution of those 10 items? From the factor model it would say they're multivariate normal. The mean vector is given to it by the set of item intercepts plus the matrix product of lambda transpose times the factor means themselves. In our case, when the factor means 0, this term goes away. Right? It's just item intercepts. The covariance matrix is given to it by lambda phi lambda transpose plus psi. This right here is, like if you're ever walking around a quantitative methods conference and you have that on a shirt, everybody's like, high five. Way to go, right? If you need an idea for your next tattoo, I humbly suggest to you that. It's a classic when it comes, I try not to talk about it in here much, but when it comes to statistics, this is a classic. Like this is right up there with x transpose x inverse x transpose y. Like this is the equation. This is the covariance matrix under the assumption of a normal factor model, CFA model, right? But with all of that, we can actually go and show, using multivariate normal distributions, some matrix partitioning. You ready? Here it goes. We can show the factor mean under a CFA is actually given by this equation right here. It's a closed form, meaning if you estimate your CFA model, let's say you're using M plus, not estimator equals Bayes, just M plus, right, or Levon. You can estimate your model parameters, your item intercepts, factor loadings, unique variances, factor means, factor covariance matrix, all that. Then if you want to go and give everybody a score, their EAP estimate of the score is given by this matrix product right here. It's weird. Let me give you the core of it. The core of it is the difference between each person's item score and what the mean of that item should be. Right, so how far a person deviates from the mean of the item is the core of a factor score in the CFA model. And it's weighted by certain amounts of variation and then the overall factor score itself. So it's like a residual of some sort if you think about it, because this right here is a residual between their scores. It's a weighted residual. The variance-covariance matrix of people's scores is also obtainable. Again, if you're interested in this and you want to know more, I encourage you to look at these slides or come talk to me. It's an interesting phenomenon. But what does that tell you? It tells you that under the assumptions of normality, one of the reasons why we keep CFA around, even though it doesn't really apply to these items, is that we can do things like this with math. There's one mean, there's one covariance matrix. This also tells you the following. Look at this. Nothing about the data appear in the covariance line here. So what that means is if you have everybody with complete data under this frequentist result, the covariance matrix of your factor scores is constant. Put a different way. The diagonal of that covariance matrix is the squared standard deviation, the squared posterior standard deviation, the posterior variance of a factor score. So that means that everybody's factor scores have the same variance or standard deviation in a CFA. We can show it with math, right? Kind of cool. Now you think about that from an IRT perspective, that's not the case. The graph of the expected value of theta by the standard deviation or standard error of theta is not constant unless you have a very flat and very wide information function, right? The information idea that we talked about before in other classes. Which is why this plot threw me for a loop. That on the bottom, the x-axis is the mean, the y-axis is the standard deviation. And using normal theory, I told you the standard deviation is constant. But there's some variability in it here. Why do you think that's the case? Anybody online want to think too? Yeah.
Because CFA assumes the item response follows normal distribution, but our data is not normal.
In this case, that's not the reason. It's a good idea, good guess though. Our data aren't normal. However, there's no way to tell the data to tell. It just makes that, it imposes that assumption, like the way the math works on it. Yes?
That may be, well, because we have fluctuation in the posterior distributions with chains. No?
That's it. Think of it this way. Each of these equations are full of matrices of model parameters. The posterior distribution I'm showing you here, those model parameters are changing. They're being estimated. All right? So when they're being estimated, we might have fluctuation in those, systematically or otherwise, depending on how large our sample size is, right? The posterior standard deviation of these parameters, item parameters, the width of that is directly related to the sample size we have. In our case, we have 177 observations. So, using that as an example, I did some investigation. Now, this investigation is not in the slides, but I wanted to talk about it because I think this is an important part. I didn't see this in Bayesian stuff I had read, although I'm sure people have talked about it. But let's imagine we fix our lambda parameters to their EAP estimates. We fix our mu parameters to their EAP estimates. And we fix our psi parameters to their EAP estimates. Okay? So then I created some stand code where I import our EAP estimates of each of our sets of parameters, and I use those in our analysis. So these are not now not estimated. The only model parameters being estimated in this model is the person parameter, theta, the latent variable. Let's see what happens. Of course, you got to wait. Now, to run this, because we're going to be dealing with some pretty small numbers in just a moment, I'm actually going to run a very long chain. And the reason for that is I want to be able to see the distribution. I want to get a good summary of the width of each posterior distribution. So the longer the chain, the more n goes into that standard deviation that we use to describe it, right? The posterior standard deviation. So I ran this 50,000 times. It's a bit overkill, but let's take a look. It will not, by the way, I'm going to do some plots comparing what we did here with what we did in the previous step. So you're going to see that running it longer is not actually going to have much of an impact on the posterior estimate of the mean, but it will have an impact on the standard deviation. And it's almost there. Now get this though, for us to get the actual summary statistic of the mean, that actually takes longer, just about as much time as otherwise. But do you see what I'm doing? It's just to recap again while this talks. This plot shouldn't happen and wouldn't happen if we ran this model in Levon or M+, where we use just a regular normal theory maximum likelihood factor analysis. We would have the same standard error for each factor score regardless. It would be a flat line. And I want to make this point because there's this subtle issue in Bayes. When we allow any uncertainty into our parameter estimates, that uncertainty in our item parameters actually gets expressed as uncertainty in theta. So remember that if you're an educational measurement, when you give people scores, how much error are in your item parameters. Because if you ignore that, you might be overly confident about what their thetas are. But let's take a look. It's coming. Go, go, go. You see what I'm doing? Anybody have questions about this whole approach? Okay. It is coming. I promise. Anybody want more candy? Believe me, I will eat it all. I have this impulse control problem, so let's just put it that way, around food. It's a polite way of putting it, right? It's another way of saying I can't stop eating when the candy is there, right?
I have a question.
Yes.
So I think this is kind of related to the question I asked you earlier. So if you have like tens of thousands or hundreds of thousands of estimates that it's doing, and then you want to work with those estimates, can you subsample? Like, how would you approach that so you don't ask the computer to do like millions?
Well, it depends on what you're doing. Can you do a simultaneous model analysis first? That'd be my first thought.
Okay.
And if not, take a look at my website for slides on how to do it otherwise.
Okay.
It's outside the scope of what we're talking about here, but yes, you have to worry about it.
Yeah.
There are sort of data combination approaches to thinking about it.
Okay.
So what I'll have up here, this plot is a plot of the mean or the EAP estimate of theta by the standard deviation estimate of theta for our case of having fixed item parameters. And you'll say, Templin, they're not all the same. You're right, they're not all the same. But look at the range. They differ in the third decimal place. Right? It's small. Right? So it's starting to behave like we had expected it to. Still not exactly there, but it's close. But now let's compare these estimates with what we had from where we estimated the items also. I'm going to grab the parameters from both of those. This is a plot of the fixed item parameters versus estimated item parameters for each person's point estimate of theta. It's pretty spot on, isn't it? The mean, the factor mean is the factor mean is the factor mean. This is the plot of what happens when we fix our item parameters versus our estimated item parameters for the standard deviations. And you see right here, these are not the same. Right? So what am I trying to tell you here? The reason why we saw the plot that threw me sideways previously, that one, is because we're estimating item parameters simultaneous to estimating theta. And believe it or not, I'm going to post this paper next week. There's a paper in 1999 by a guy named Rich Pates and another person named Brian Junker, Pates and Junker. Pates was Junker's student at Carnegie Mellon. Pates has been a VP in different companies. He's well known. Junker is a fantastic scientists in this area. Both of Junker went to Illinois. Anyway, I shouldn't say that. Iowa, right? But that being said, in their paper, they described, basically they built a Metropolis Hastings algorithm for IRT models, right? And they showed how you could implement it. I think it was in S+, a package that still exists, but basically R has ripped off and made open source. In their paper, they talk about the issue of theta estimation, and they suggest fixing the item parameters and running the estimate a second time to estimate theta. And that's how, I had this kind of blindly, didn't really think about that much. But now as I go on further in my career, I think I actually like this approach a little bit better. Why should we not include error in our estimates of item parameters when we're estimating a person parameter? In particular, the other thing I want to point out, the lower bound, when we estimate our item parameters, the smallest value is somewhere a little under 24 for the standard deviation, right? The highest value when we fix the item parameters is below that. So we're talking about how much error there is in theta. We're not talking big differences here, but we're trying to be as precise as possible, right? If we fix our item parameters, the range is like that. If we don't fix, all right, I'll do that right there. Visual, here, I'll show it right here, right? If we don't fix our item parameters, the range is like that. But the ranges don't overlap, right? So if you're thinking about this and thinking about doing the most conservative approach to describing data, right? Better yet, for those of you in ed measurement, we have a standards. The guide, for assessments, it's APA, AERA, NCME have a guide to how we do assessment practices, right? And we're supposed to have conditional standard errors of measurement. I'm going a step further, right? We're trying not to lie with our assessment. Why wouldn't you include the error in your item parameters when estimating theta? That's what I want to know. To me, it makes more sense because we're claiming when the variance in the posterior standard deviation of theta is higher, what we're saying is we know less about a person, right? But look what we just did. We ran two analyses, one where we fixed item parameters, one where we didn't. And when we didn't, all the standard deviations were higher, right? So I look at it now like thinking, I think all of our analyses should think about this as we go forward, when we do things. Because otherwise, we're sort of ignoring error on one side, which doesn't make a lot of sense to me. What do you think? Huh? Don't disagree? It's okay. What does that mean, though, from a Bayesian sense? It means we need more items to make better conclusions about people, right? It's just hard to do that. All right. Any other questions on that? Okay. No questions? Let's go back to the slides. Okay, I think we did that. Next part of the slides, estimation fails. What do I mean by estimation fails? Turns out, I think I mentioned this before, when I used my code and I set the random number seed to this number, I got the results you saw. When I changed it to this number, I didn't get those results. Now, underlying this issue is the fact that we don't often talk about this, but when you look at the linear model for factor analysis, IRT, whatever, whenever we define lambda times theta, that value that's in the core of our model function that serves as the mean of the normal distribution for each item is equivalent to an opposite definition where all the lambdas were multiplied by -1 and all the thetas were multiplied by -1. Right? It's like saying, remember this is the gambling tendency, or not gambling, the tendency to believe in conspiracy theories, data, right? The tendency to, so it's like on this side, this is the more theta is, the more someone believes in conspiracy theories. On this side, the more theta is, the less they believe in conspiracy theories. Right? It's just a flip of the scale. It's like reversed almost entirely. Right? And I mentioned before how estimation programs have this they have to start randomly, and they get sucked into a mode and can't get out. It's sort of like a black hole, right? So I want to show this real quick here. So I ran this analysis. All right, so I'm going back here. Here's our analysis. Here's that random number seed. There is our maximum R hat. And these are our estimated item parameters. So you'll note the intercepts look fine, residual variances look fine, but these factor loadings, what's up with those? What do I mean by that? I mean, look at the values of this, right? They're close to 0, and their R hat is all over the place. And then we look at the latent variables. They're all close to 0. Look at all their R hats. Some of them are okay, like this one right here is okay. But look at that, right? So let's take a look at the trace plots real quick. Remember, the trace plots are the MC-MC chains themselves. All right, this is 4 chains. Turns out, see if I can zoom on this. Some zoom, all right, way to go here. There we go. No, I need to make it very big. Turns out, if you can see a little bit closer here, there are 2 chains down here, and there are 2 chains up here, right? And what's happening is that these are mirror images of each other reflected across 0. It's if in 2 chains we had -1 times lambda, and in 2 chains we had just lambda, right? This is the problem I was telling you about. We can see that also in the density plots, the distributions, symmetric about 0, right? And if we look at thetas, theta 1 looks fine, although it's very close to 0. But look at theta 2, its density is almost also reflected about 0. And then finally, because I like this plot, remember the plot of the expected item response function as a function of theta? So I made that plot. I'm going to vary a theta between -3 and 3, but then I drew all the trace lines from our MC-MC chains, our chains themselves. This is for item 3 here. This plot looks like that. Right? Big old X, which should tell you, no, this is terrible. By the way, okay, so long story short, I have a few grant projects, and I was doing grant analyses yesterday for one of them. I know one of you knows what I'm talking about. And I didn't stop this from happening, and guess what? The first time I ran stand, took an hour. That happened. I had with factor loadings or discriminations. So how do we fix it? All right, here's all this also with the slides. So the fix for it. Some of you will say, change the prior distribution to only be positive, right? Sounds nice. So much phone call. It's nice ringtone. Very soothing. Right? Have you heard that before? We could just fix the prior distribution to be log normal for all the A parameters or the factor loadings. That's fine. You could do that. That would fix it somewhat. However, there's 2 drawbacks to that. Number one, those prior distributions that are strictly positive sometimes are really weird where the mass is, so you'd be putting undue pressure on some of the parameters that you're not familiar with. Problem number 1. Problem number 2, we may want some of the thetas to be negative, some of the lambdas to be negative. That's an informative choice in this type of model, right? Particularly if we had like a reverse-coded item that we didn't modify through a transformation. right? That value will be negative, right? The opposite. We'd want to see that. So I don't like the idea where people put strictly positive priors on these parameters that occasionally should be negative or will be negative. It's sort of like, it's like using a sledgehammer to fix a problem with a regular hammer would fix. Like I'm trying to hang a picture on a wall, got a nail, I need to hammer the nail in, and all I have is a sledgehammer to do it, right? It's like overkill, right? It's too much. We don't need to do that. We just need to recognize why it's doing this, right? And why it's doing this is that it is randomly starting in a way that the thetas and the lambdas flip their meaning. So we just have to stop that random start process and tell them to start on the right side. So it turns out you can do this by setting some starting values in Stan when Stan starts its code. What do I mean by starting values? Remember, all the parameters have to have a random value when the Markov chain starts. And then through the magic of MCMC, they get on the convergence train and they all eventually reach convergence or something like that, right? Stan, when this happened, I had to go deep into the Stan documentation because, how many of you have been like eyeballs into Stan documentation? I have, let me tell you. So I was like, I didn't see anything in the Stan documentation about how you do starting values. And then I found a little bit of a breadcrumb on RStan. Remember, Stan itself, no, RStan is the interface of R and Stan, but we're not using it, we're using CMD Stan R, right? So it made me think, okay, so what needs to happen is we need to get the starting values generated in R as part of this function. So it turns out in CMD Stan R, there is a way to make this happen. And I'll show you that. The other part that you can talk about were those other priors. In Stan, had we put this lower bound on lambda, that would have done it. But I don't like the lower bound, right? A lot of people, in fact, more people put the lower bound there than don't. I think that's just bad practice. I really do. Think about the algorithm, think about the modes, push that way. So, how do we start? What happens? First of all, in Stan, if you define a lower bound on a parameter, for instance, this psi parameter is a standard deviation. It can't go below 0, right? What Stan does with that parameter is it transforms it so that it's not bounded, right? So remember the idea of the link function before? It's basically putting a function on that parameter and sampling the unbounded space. Doing this all without you knowing it, which is fine, because they handle the transformation, they handle all the differences in posteriors and so forth. It's well done. And then on that unbounded space, Stan randomly starts every parameter between -2 and 2. Seriously, every parameter, whether it's 80 million, whether it's 0.1, everyone starts between -2 and 2. It still works, right? Starting values will still, any random set will work. What we have to do to fix this is that we have to fix one of these sets of parameters so they're the right way. And in our case, I want to focus on lambda. We want the lambdas to generally be positive if they should be positive. And if we start all the lambdas so that they're all positive, and I don't mean just a little positive, I mean a lot positive, then we'll flip the algorithm to converge to the mode that we believe should be the case, right? The higher the theta, the more belief in conspiracy, right? So how do we do that? Turns out there's an init option. Remember how we build this model CFA and we use the sample function right here? The init option allows us to randomly sample our parameters. There's very little documentation on the init option, though. So I'm going to walk you through how I figured this out. And I'm doing this, by the way, because I'm leaving, the documentation is like breadcrumbs sometimes, right? And honestly, I'm sitting there going, how on earth am I going to build these slides in the way I really want to? And I almost gave up and just said, just do the strictly normal. I'm like, no, You all deserve more. You demand more of me. I need to step it up. So let me show you how I did the detective work, because you may end up in a spot where you need to do detective work at some point too, okay? All right, so this right here, this is a function. What it does is it's calling, and it says any parameter named lambda in my model, it's going to use a starting value from a normal distribution using the R function, rnorm. I tell it the mean. Here I'm starting at the values at 10. Remember, the lambdas all had values that were positive, but they were between 0 and 1. Starting at 10 won't hurt us. It'll make the chain have to run longer. They'll have to take more steps to get down to where they should be. But remember, we want these things to be very positive to keep the things in line. But by starting it with a random normal, again, I'm allowing random starts. They're just all positive numbers, right? So I'm still allowing, if there's some other problem with the posterior distribution, the random starts will hopefully help us pick this up. Now, here's what I did to sort of test it. I wasn't sure what I was giving it was starting as starting values. So I started this, and I set the warm-up to 0. And I wanted to stand for one chain with 10 iterations. And the reason for that is, if I have 0 warm-up, I will see the very first values. Well, it turned out Stan has to have another option if you have 0 warm-up. You have to turn adapt engaged off. It'll warn you and tell you that. So I did that. All right? It doesn't like that. But now I can take a plot of this, and I can see where those starting values are. And look at that. Each one is a very positive number. Right? And if I format this a little bit better, if I show you it in RStudio, you can see the actual values for each. So now I'm starting lambdas at a ridiculously high number, but they're all positive, right? So I could confirm that my starting values sort of took hold as I did this. So now I wanted to run the chain with a little bit of warm-up, but then keep track of the values to see how long it took the lambdas to move to where I thought they should go. So I ran a 10 iteration warm-up, 2,000 length chain. And now I'm going to plot the trace plot, the time series caterpillar plot for each of the lambdas.
Is there a reason why you changed your standard deviation to 2 in that second one?
I was fiddling around. I
Right.
probably should have just left it at 2 the whole time. But take a look at this right here. Actually, let's zoom in on just one of these. You can see they all kind of look the same. They started really high, and then within very quickly, I don't know how many steps it was, by 200 or 300 iterations, all chains had started to converge to where they needed to go. Right? That's what I was trying to confirm. Was I getting caught somewhere? So whenever we do starting values, whenever you think of starting values, you may have to experiment with it. And turning off the warm-up is an easy way to do that. Don't run a long chain, just run a few steps and see what's happening, then run a little bit longer chain. And now I can run that same 2,000 length warm-up, 2,000 length chain, and what do I get? The maximum R hat is back to 1. It worked. And if I print the model parameters, you will see their values are about the same range as we saw before. Same with theta. Let's get that taken care of. Each of the thetas here have an R hat of 1, so we're all happy about that, right? Then I wanted to plot, I'm plotting all of the parameters now as a scatter plot. I'm going to plot all the parameters from the analysis I ran where I had the original seed from today, the random number seed, like the results I was showing at first, against what I had just plotted here. I want to show you how different these results are. And now this plot will contain theta, lambda, mu, and psi. They're all the parameters all together. Here's what you get. Dun, da, da, da. Doesn't matter which parameter it is. They're all right about the same. What is this telling us? Right? By picking the starting values, I didn't affect much of the posterior distribution, right? In fact, if you want a numeric value to describe this, the correlation between of all the parameters, the EAP estimates of all the parameters with each other is 0.999958. That's about as close to 1 as you're going to get, right? Pretty close. So I'm showing this to you to tell you the starting values, by changing the starting values, to sort of suggest evidence that there's these two modes in effect for what we're doing. And by starting on way above the other mode, we converge to the one that we want it to be. Did I see a question?
These are the means.
Yes, the posterior means, yep.
All right, I'm there.
Yep. And now all the I just, like as a quick and dirty check, if I was doing something, if I changed the prior on this, we wouldn't see this, right? Because the prior would now have an impact on all the parameters. And we don't have a very big sample size, so the prior might have a large impact on the parameters. So where am I going with all of that? All right? Here, just in time. Now I don't have any lecture for Friday yet, so I gotta build that tomorrow. It's kind of nerve-wracking. But here's what we have. I showed how to model observed data using a normal distribution. Right? The assumptions of confirmatory factor analysis, clearly not appropriate for these data. And we're going to change that assumption next week. When it's not appropriate in Bayes or in anything where you have a likelihood, change the distribution, change the likelihood function. Right? It's no longer I can't fix it, it's I'll just change it. No problem. Throughout this is very important. We're going to have to use those initial values. Otherwise, the multimodal nature of this will happen. Right? I mean this. I was just working on a project for the Dimes grant I'm on yesterday, and this was happening. And I'm like, oh, wow, it really happens a lot, right? And in other programs I've used, it was less so. Behind the scenes, if you're coding this yourself, you just know to start the starting values in one direction randomly. We're still going to have to continue this as we get into the different types of data we have. Right? So next time, we're going to talk about item response theory. What's the distribution for the item? How do we define our parameters? Oh, wait, there's that whole discrimination difficulty versus slope to intercept. We'll go from there. And then we'll do categorical distribution for observed data. By the way, how many of you are in Lisa's class again? What do you think of thresholds?
Confusing.
Guess what? What if I told you you have complete control over how you specify your model parameters? And if you want an intercept, you specify an intercept. And if you want a threshold, you specify a threshold. Because in our model, we have that part in stan where we have to tell it sort of a linear combination of our data. And if we wanted the threshold there, we would just change one of the signs to make it work. So you can specify it your way. What's that fast food place, Burger King, have it your way? It's like the Burger King of, never mind. I think I'm talking about. All right, we're out of time. Thanks everybody for being here today. Thank you to online. If you get a frantic email from me Friday morning, I don't have slides for today, I apologize in advance. I'll try. And for those of you in person, help yourself to candy on the way out. Good to see you all. Take care.